saw that the controller K can be a PI controller, and how we can get the parameters of the PI controller Ki and Kp we just now discussed. I want to introduce one more concept called the feed-forward control, which will help the PI controller to be more robust and faster. So let me have this XY axis. On the X, I am going to have the duty cycle D. On the Y axis, it is V0. So V0 and D are related. V0 is the output of the buck converter, and that is the controlled variable. D is the input to the buck converter. It is the control input. So the relationship is D is control input. This is the controlled output. And actually, when you talk of transfer functions, it is V0 by ds in the Laplace domain. So these two have a relationship. So let me draw that. The slope is Vi. So Vi into D. So let's say, for example, D varies from 0 to 1. And let me take an operating point where this is the operating point and this x-intercept is D. I will put it as uppercase D, and the y-intercept is uppercase V0. So the relationship between V0 and D is V0 is equal to D into Vi. This slope of this transfer curve is Vi, which is fixed, constant. So V0 is D into Vi. D is actually the control input. So now let me say that due to many reasons, Vi itself can vary. So therefore the slope of this blue line can vary, or there could be a disturbance in the output, or there could be some disturbance which is reaching the output, and V0 can vary. So therefore this operating point can vary in the neighborhood of this steady state operating point that we have shown here. So let me say that D is actually not D, but D plus or minus D hat, the small indicating the small variation above the neighborhood, about the neighborhood of the operating point as D hat. And likewise on the V0 side also, on the Y axis, I will say that this is V0 plus V0 hat, where V0 hat is nothing but the variations in the neighborhood of the operating point. So in the normal PI control that we discussed till now without the feed forward control, the controller, okay, this I will just write down D is V0 by Vi, and this is coming from the model where V0 is a specification and Vi is measured from the circuit. Now why this is important is that all these variations, all the variations in control input variation D is supposed to handle the complete variation of V0. So the PI controller that we discussed till now is supposed to handle all these variations, which means that the operating point can swing between 0 to the actual operating point, and the PI controller is supposed to handle these large signal variations. As opposed to this, with feed forward control, what is it that we are going to do? We are going to use this. We said that this is the model of the system. We know that V0 is equal to dVi. We have developed this model earlier while studying the buck converter. So I know V0. V0 is coming from the specs, user specs. Vi is coming from the measurements, instant by instant measurement. So V0 by Vi is known. So this is the nominal operating point or the steady state operating point that the system should be for that given Vi, for that measured Vi and specified V0. So this information is available to me. Let me use that information which the PI controller was not using before. So you use this information and set the operating point at this. Then due to any disturbance, if there is any variation in the neighborhood of the operating point, the PI controller should only handle these small deviations. So D hat and V0 hat only the deviations about the neighborhood of the operating point that the PI controller has to handle. So these are small deviations and therefore the PI controller is much faster to handle the small deviation. And also because of the feed forward term, this is the feed forward term which is giving guidance or direction to the controller that any major deviation it is supposed to come and settle there. It will be more robust. So this way it is more robust and faster. So let us see how we include this feed forward term into our control. Let us now incorporate the feed forward part of the controller into this system. So I have the controller as it is existing now. Now you see that K is nothing but the PI controller, and this PI controller is handling the entire large signal swing of V0. Now I will remove that because I need to include feed forward portion also apart from PI. Let me extend that, make the connection, and here I will include the PI controller. Now this PI controller has two parameters, Ki and Kp, which we need to select just like as I told you. First make Kp 0, Ki you gradually increase from a very low value to take the parallel with low bandwidth, and keep on increasing till you get a very good response, time response, and then fix that. And after that increase Kp from 0 gradually to pull up the transient performance. So this is the error, and the output of this is connected to another summer, and that is where we attach the feed forward term. And that feed forward term is the steady state duty cycle, the uppercase duty cycle, steady state duty cycle, which will decide the nominal operating point or the steady state operating point. Now what is being fed back is V0, the nominal or the steady state V0 plus the disturbance or the variations in V0. Deviation in that V0, V0 reference has to contain only the nominal steady state operating point V0. It doesn't contain the deviation because this is the reference. So this minus this would give you the error, which is basically the deviations about the nominal operating point, about the nominal steady state operating point. And the controller is supposed to take care of this and make this deviations 0. So you see that PI is now only handling V0 hat deviations, small deviations in the neighborhood of the operating point. And what is the output of the PI controller? The output of the PI controller is VC hat. Now VC, uppercase VC, which is a voltage which is proportional to the nominal duty cycle, is given at this point, and this VC hat is proportional to D hat, which is deviations about the nominal, because they are all proportional to time. Now on adding these two, you have VC plus, so I have VC plus VC hat, the voltage proportional to the nominal duty cycle, plus VC hat, which is the voltage proportional to the deviation in duty cycle, so is together proportional to D plus D hat. So that is the voltage signal which is actually going to get modulated with this particular carrier, triangular carrier, and that PWM is driving this gate and switching on and off this buck converter transistor. So you see here the PI controller is only handling the hat terms. It is only handling the deviation terms, which is small signal terms, and the nominal steady state operating point is given from the model, because D is equal to V0 specified by Vi measured. So D is a feed forward term here. This handles the steady state part, and the deviation, any deviations, any disturbance, PI takes care, and it is handling only small signal deviations, and therefore this PI will be very robust and very fast because the deviations are small. So in this way you can introduce the feed forward term and make the controller fast and reliable.